Well, good morning, everyone. My name is Katie Singleton. I'm the team leader for the survey team from the Oregon Institute of Technology, better known as Oregon Tech. We are out of Klamath Falls, Oregon. I'd like to introduce the rest of the team here. We have John Henning, Riley Edwards, Saul Preciado, Mosier Locke, and Marcus Helm. We also would like to throw a big thank you to our advisor, Geomatics Professor Mason Marker. We really appreciated your logistics support over the past few days. I call myself the team leader, or we call you the team leader, but I want to emphasize that this truly was a team effort. Everyone pitched in according to their strengths. To give you some examples out in the field, I was the one reading through the level most of the time, but John was our man on the rod. Saul was a great note taker and bookkeeper, and the rest of the guys had the really hard work pulling that steel tape, so thank you all. So before we get started, I'd like to share with you a brief outline of what we'll be telling you today. We'll be starting off with some of the pre-planning that we did once we found out what our task was, and that will include some discussion of how we decided to set up our parcel, as well as how we decided to make sure that our parcel was actually square. And we chose to use triangles to do that, right triangles, as well as our decisions about creating a grid layout for the topographic data that we collected. We'll also walk you through some of the field work, including how we established a basis of bearing, how we decided to configure and actually set those boundary corners, and then the topographic work that we did to map the parcel. And we'll also give you some idea of the calculations afterwards. That's including how we reduced our field notes, how we chose to resolve the boundary, and also how we developed the topographic map. So I'd like to hand it over now to John.
So we had a meeting Saturday night after the mixer to determine what procedures and methods we were going to use for our field work and our office work. The parameters we were given were to lay out a 1 square acre lot and associate a topo map with it. For the boundary part of the project, it was determined that we would use right triangles at 30, 40s, and 50s to lay out all the grid lines possible and to lay out the boundary lines. We decided to use an assumed coordinate system and an assumed north to make calculations easier post-field work. For the topo aspect, we decided upon a grid spacing of 25 feet, which would hopefully provide us with an accurate enough surface model given our time and restraint out there. We believe 121 shots would be enough to give us 1 foot contour intervals and to represent a good surface. And now, if Marcus would like to take over for, Riley, to take over for the field procedures.
So we did have a plan going into this, but of course nothing ever really works out how you expect it to. But to start off, we're going to go back to the basis of bearing, and to do that, we had a handheld compass where we could set the declination, and we set that, and on that line, we figured out that it was going to end up being perpendicular to our north line, and knowing that it's going to be a right angle, we used a 30, 40, 50 triangle to get the line for our north line. And how we did that was we came back towards the center point, or we call it the benchmark, and 40 feet, and then we ran 30 towards one of the corners, and so we had a hypotenuse angle, or not angle, a distance of 50. So where the 30 and the 50 meet, that was just a point on line. And once we had that point on line, we set the level up on that midpoint of the north line, and so we could get the direction of the line. And so once we had that direction, we pulled tape from the midpoint to the corner and arced it, and we also did that from the benchmark to that corner and swung it, and where the two arcs met, that's where we put our point in the ground for the corner. And after that, we went on to our topo, and how we did that was once we had all of our boundaries, we pulled the tape across the north and south to get we did A, B, C, and then on the east and west, we did stationing. And so we did 25 feet through the ABC, and then we did stationing the other way. And we tried to do the 25 by 25, but the features didn't really allow that to happen exactly how we wanted it to. And also, when we were pulling tape, we also calculated the sag, and there's a lot of different information or variables that account for that. And now I will go and let Saul take over.
So I was responsible for taking the field notes, and field notes, as we all know, have to be accurate and clear. And the importance of that in accuracy, that doesn't mean accuracy of numbers. It means accurately reflecting what the work done that particular day by that crew. And you have to include sketches, and the sketches need to support the data that you collected. Of the two slides, or the two pictures that you see on that particular slide, they're the most representative of the two portions of the survey that we did. The left one is the beginning of the boundary resolution. The left page is the data that we collected when we were doing the 30, 40, and 50-foot triangles. The sketches on the right are simply the orientation of what quadrant we were going in to establish that particular line. The example on the right is the very first page of our topo grid, and we ended up getting quite a few points beyond what we initially estimated. And so that's the data, and then on the right is the grid layout. And what we have is on the east-west line, we have letters, and the north-south line was stationing. Finally, as we all know, records can sometimes be called into court, and when this happens, because this happens, all our errors that we have were just simply lined out and not erased, so that we would show that nothing was hidden. Now I'd like to pass it over to Mo for some calculations.
Sweet. So the next step in this process of completing the project was the office calculations. So we started by reducing the field notes, which included calculating elevation and coordinates for each of the points that we took along the grids. We did this using Excel spreadsheet, and then we calculated the coordinate system, which facilitated just kind of where things ended up in the map. For resolving the boundary, we held distances over angles. We figured since we're taping everything, we don't have an actual way to measure or accurately measure the angles. That should be held paramount. We tried to implement a trapezoid solution for resolving the boundary, but least squares adjustments ended up being more precise for what we were wanting to do. So we held distances over angles again. We set the angles to be free, and we ended up passing the chi-square test using this method. For mapping the topography, we had almost 200 points, and we mapped it in Carlson. We utilized a field to finish routine, so that just enabled us to process the data a lot more quickly, so we could get to the actual analysis. And we were able to check our surface with spot elevations that we gathered in the field. So we pulled radial lines from the center point to each corner and measured stations along the way. Then using that elevation data, we were able to check it with our model later on. On this next slide here, we have our map. So if you have any questions with regards to that, we have it set up over there, so we can answer questions later if you have any. After this, we have the analysis. So the specifications we were given, we had an expectation of a precision of 1 in 5,000 for horizontal, and we needed to have 1 foot contours along the map. So the actual results that we got were that we had a relative precision of approximately 1 in 3,500 for a horizontal. And that's just based on our map closure and check of distances. Our elevation spot checks, 15 out of the 16 matched the surface model within half a foot, and then 13 of the 16 out of them matched within 3/10 of a foot. Our calculated parcel area came out to be 0.998 acres, which is about 100 square feet less than the desired 1 square acre. And then with the least squares adjustment, again, we passed our chi-square test and had 3 redundant observations. So here's Marcus.
Yeah, so some reasons why we got the horizontal precision we did was just because of the weather conditions. You know, all the other teams were out there. Super windy day. It was pretty hard to get that tape straight. Sag, we didn't know how much we were pulling tension, so it was kind of hard to do a sag calculation without knowing the exact tension in which you were pulling at. And a slope distance versus our horizontal distance, you know, when we have both sides pulling, at times one side be a little higher to get it over different terrain than the other side. So instead of getting that exact horizontal line, we were actually getting a slope distance line. And we didn't use angles. We actually held distance measurements over angles. For our vertical precision, with that wind blowing as hard as it was, that rod was almost impossible to keep it perfectly perpendicular with the ground. When you had more than one section up, it would start to bend with the wind a little bit. Just the uneven terrain also made it a little bit difficult to keep it up centered. And our grid method, it can't capture every undulation of the surface. So some challenges. Again, the weather conditions. As you can look in that picture, if you can see it, that tape has a pretty good bend in it, pretty good curve due to the wind factor out there. So what did we really do to break that? Well, we just waited for breaks in the winds, because at times that wind would be just still enough to get as much as that bend out of it. And also with that wind blowing as hard as it was, we couldn't really hear each other, so we set up a communication relay between our rod man to call out the station and our bookkeeper, so there was all clarification, there was no uncertainty what was being said and and wrote down. Our equipment, we actually had our 300-foot steel tape break on us. Thank you, Mosher, for fixing that. We were unable to reel it up and pull it back out if he wasn't able to put unable to get it fixed. Also, another challenge we faced was not being able to use the azimuth ring. So to accommodate for that, like we said earlier, we just held distances and took no angular measurements. We also had obstructed sight lines. So what we did to do that is we used triangles. What we wanted to do from the beginning is use one triangle to set up one side and then get line of sight to get that straight line to the next point. But we weren't able to do that with some of the stuff in the way, so we actually ended up setting up 2 triangles to make that work, so one on each side of the midpoint. We also had to temporarily move vegetation, and what I mean is that some of those big bushes out there, they were flexible enough to actually bend out of the way so we could get a measurement for a line of sight, just long enough to get a reading. And then also, we had the whole team at times pick up the entire tape, move it in our 25-foot intervals so it wouldn't get caught on the brush, and just kind of make it easier to move so we didn't have to wind it up and then put it back out every time. And with that, I'm going to give it back to Katie for our lessons learned.
All right, so I'll wrap up our little section of the presentation here. As Marcus hasn't told you, we definitely encountered some challenges with this field work and with the office calculations afterwards. We believe that we came together as a team, worked together out in the field to solve some of those problems as we came up. But that doesn't mean that there's not some things we wish we could have done differently. Absolutely. So some of the things next time, if we were to do this again, we would want to practice pulling the tape with a constant tension. We did practice, but we didn't have, there was no way to really practice for that sort of wind. So we would want to get a better feel for the tension in the tape. We would also want to include more redundant distance measurements out in the field, since we did decide to hold distances. If we had been able to get some distances from our midpoint benchmark out to the parcel boundary midpoints, we could have really strengthened that least squares adjustment a little bit better. And we could have analyzed the topography a little bit better for some of our initial setups. If we had chosen a different initial partial corner to site, we might have been able to see all the way down that north line, which is the first one we set. But the terrain just didn't quite agree with us on that one, so we ended up having to use additional triangles. And the last section we want to leave you with here is just some of our reflections on how this project really connects with the theme of the competition, and that is surveying service. We did certainly consider this like an Engineers Without Borders style project. And what that means is we have to learn as surveyors how to adapt to unpredictable situations. That wonderful equipment that we're used to using, we might not be able to use that in a developing country if they don't have the infrastructure to support it. And even here in our own work, sometimes things go wrong and equipment breaks down, so we need to be able to adapt to situations as they arise. And also, we learned that we can't rely on the equipment to do the work for us. We can't treat our GPS units as a black box where you just punch numbers and punch buttons and have numbers come out. We have to know what those numbers mean. And so this competition really helped us kind of strip back down to those foundational surveying concepts. We at Oregon Tech say that surveying is both a science and an art, and we believe that this competition made us a lot better artists. So thank you, and if you have any questions, we will welcome them now.
accounted for SAG, right? So you used that formula?
Yes, we did.
Was it an assumed full tension that you guys used?
Yeah, sir.
Mhm.
Sorry. Yeah, so we had assumed pull tension of about 20 pounds. We use that as an assumption for all of our calculations due to SAG.
Okay.
How many times did you guys pull the distance between one point and another point?
Well, we started out, we did, I believe, 2 perimeter checks, is that correct? The first one was after we did the initial setting of our points, and then we completed our topo and did a final check at the end. And we believe that we had it closer to a true 20 pounds of tension on those second set of calculations, and that's what we used for our precision calculations and the actual adjustment.
Did you notice any impact on the compass readings that you took due to local influences, equipment, and so forth?
Yeah.
No, not for the most part. I ran the compass most of the time, but it seemed to be pretty true. And what I try to do, because normally when you're in a surveying vest, you have nails and everything in it, so you try to hold it out in front of you to get rid of any problems that might cause. So running the compass, I didn't see any problems whatsoever with any of the readings.
Yeah, we also took several redundant measurements there. We measured from our benchmark out at the desired bearing and then walked out online and measured back to make sure we did that, I believe, 4 times. And it all seemed to run true.
Any other questions? Okay. Thank you very much.